Okay, so we've already mentioned the concept of the molar mass of a substance. So we're just going to review that here quickly. So the molar mass is often indicated with an uppercase M, and then sometimes people will write the formula for the substance as a subscript. And the molar mass will have units, grams per mole. Now the molar mass functions as the conversion factor between the mass of something in grams and the number of moles of something. And when you're going to moles, you're going to multiply by 1 on the molar mass, and when you're going from moles into grams, you're going to multiply it by the molar mass itself. So it's a pretty simple concept. Sometimes people will indicate the number of moles of something with the little symbol lowercase n. N, it's the number of moles. And a simple way of remembering how to calculate the number of moles n is that you can take the mass in grams and you can divide by the molar mass. And that'll very quickly give you the moles of something. Alright, so let's see how we go. So the formula mass of a compound is simply defined as the sum of the atomic masses of all of the atoms that are present. So you've seen this before. If we were to want to calculate the formula mass of C2H4, we would add together the masses of 2 carbon atoms and 4 hydrogen atoms, and we're just going to get those masses from the periodic table. So if we have a compound, then 1 mole of a compound weighs an equivalent number of grams as its formula mass in AMU. So if I calculate the formula mass of a single molecule of H2O, I would add together the masses of 2 hydrogen atoms and 1 oxygen atom, getting those masses from the periodic table, and that would tell me that a single molecule of H2O had a mass of 18.016 AMU. What it also tells me is that a mole of water molecules would have a mass of 18.016 grams. Or more commonly, we'll say the molar mass of water is 18.016 grams per mole. So the molar mass, as I've mentioned, I think at least twice now, functions as the conversion factor between mass in grams and moles. So knowing that the molar mass of water is 18.015 grams for every 1 mole, we can reorganize that into 2 conversion factors, one that has grams on the top line and one that has moles. Just like any conversion factor, there's always 2 ways of writing it, and the way that we write it is going to depend on the conversion that we're trying to do. So if I wanted to turn grams of water into moles, I would need to multiply by the conversion factor that has grams on the bottom line and moles on the top line. So I know that to convert between moles and grams, I'm going to use the molar mass. And so in this case, I need to use the form of the conversion factor that has moles on the top and grams on the bottom, like so. So 2.54 grams times 1 mole per 18.015 grams, and that ensures that grams cancels out, leaving me with moles. Alright, this is all very familiar, right? So what about if I want to go back the other way and say how many grams of water are there in 2.54 moles of H2O? Well, I know that the molar mass functions as the conversion factor between mass and moles, and I can go in either direction. So same deal. I'm going to calculate my molar mass. Surprise, surprise, it hasn't changed from 18.015 grams per mole. In this case, I'm going from moles into grams. So I want to use the conversion factor that has grams on the top line and moles on the bottom line. So 2.54 moles times 18.015 grams of water per 1 mole, and then that ensures that moles cancels out and leaving me with grams of water. So it's just like this. We've got the mass in grams is related to the number of moles. To do that, you need to multiply by 1 on the molar mass, and if you want to go back the other way, you multiply it by the molar mass itself. This is what we did in this problem. We went from moles to mass in grams, and we multiplied by the molar mass. Now, it's really easy to calculate the molar mass of something. You can just use one of these molecular weight calculators, and you just put your formula in there. So put in H2O, calculate, and there it is. It gave this to 4 sig figs. Now this molar mass calculator actually has a few formulas, common ones, loaded up already, so sometimes you can look there. And this molar mass calculator also has all of the elements, so if you just want the mass of an element, you can look it up there. So this is just from lentech.com, and you can just search. There's many molar mass calculators. Alright, so we can also combine the molar mass with some of our other conversion factors that we've seen, such as mole ratios. So this question asks how many grams of hydrogen and oxygen are there in 2.54 moles of water. So I've got to do moles of water to grams of oxygen, but I also want to do moles of water to grams of hydrogen. And to make this happen, I'm going to have to use the mole ratio. So watch how this works. So I'm going to use my molar mass of water again, because I want to go from moles to grams, right? And the molar mass is the conversion factor for going from grams to moles and moles to grams. So, but I also need to account that this is the moles of water, and the moles of water is different from the moles of hydrogen. So here we go, we've got 2.54 moles of water, and I know that I get 2 moles of hydrogen for every 1 mole of water. You see that? I have to account for that. And now what I want to know is, what is that mass in grams? So I can apply the molar mass at this point, and I know that I get 1.08 grams of hydrogen for every 1 mole of hydrogen. So moles of hydrogen cancels out, leaving me with grams of hydrogen, which is 5.12 grams. Now I'm going to do the same for oxygen, 2.54 moles of water, and I get 1 mole of oxygen for every 1 mole of hydrogen, so H2O. So H2O, moles of H2O cancels out. And then now I want to go from moles to grams, so I use the molar mass. 1 mole of oxygen times 16 grams of oxygen for every 1 mole of oxygen, and moles of oxygen cancels out, leaves me with grams of oxygen. So here's my grams of hydrogen, here's my grams of oxygen. As my compound only contains hydrogen and oxygen, I know that I've got in total here about 45.7 grams of water. Now, you see here this number was 3 sig figs. I only did multiplication, so all of my answers here have been rounded off to 3 significant figures. Alright, so let's kind of like, put this together in a simpler kind of way. Avogadro's number allows us to convert between moles and number of objects. So here we are using Avogadro's number. When I want to go from number of objects to moles, I multiply by 1 on Avogadro's number. So that would be 1 mole for every 6.022 by 10 to the 23 objects. And when I want to go back the other way, I multiply by Avogadro's number itself, which is 6.022 by 10 to the 23 objects in 1 mole. Okay, so MOL is the abbreviation for mole. Now, I know that the conversion factor between moles and the mass in grams is the molar mass, which is often abbreviated as an uppercase M. And when I want to go from moles into mass, I multiply by the molar mass, so however many grams present in 1 mole. And then when I want to go back the other way, from mass into moles, I do 1 mole over however many grams that is for my substance. So the nice thing to recognize is that whenever you're converting into moles, you should always have a 1 on the top line of your conversion factor. So just kind of keep that in mind. And then when you're going away from moles, you don't want to be having the 1 on the top line of your conversion factor. So that's basically how it works, and a lot of people will sketch this diagram out and then just, or copy this diagram and have it handy for when they're doing these types of chemical calculations. Now, the other thing that we saw was the use of the mole ratio, where we have like moles of one thing over moles of another thing. And we saw this where we were going from moles of water through to grams of hydrogen or grams of oxygen. So we're going to use it when there's a change in the substance. So people will often talk about going from substance A to substance B. So the type of problem that we saw in this video was a moles of A problem going all the way through to grams of B. So people will talk about things like that. And this is the full diagram. Wherever you're coming from here, you have to get your first substance into moles, and then you can apply your mole ratio. And so your mole ratio always has the moles of what you want over the moles of what you're trying to get rid of. So it depends on the direction that you're going. But we use the mole ratio to go from moles of A to moles of B. So this is the full this is the full Monty, this is the full deal diagram that we use for all of the calculations involving masses and moles and number of objects in chemistry. And you can see the 3 conversion factors that are important here: Avogadro's number, the molar mass, and mole ratios. And every problem that we'll be doing, we'll just be using this diagram. So again, it's really worthwhile having this diagram handy. And you can just go backwards and forwards. You could do mass of A to mass of B. You're going to see that that's a very common conversion, and that one requires 3 conversion factors, 1 molar mass, a mole ratio, and another molar mass. You could do objects of A through to objects of B. That again would involve 3 conversion factors. So if you know how this diagram operates, you can do any conversion on here. You can, it's very, very straightforward, provided you know how conversion factors work and how dimensional analysis works. So let's have a look at a problem here. In this case, what we're going to do is we're going to calculate the number of hydrogen atoms in 2.54 grams of water. So water is substance A and hydrogen atoms are substance B. So you could consider this as being grams of A going all the way through to a number of item B, right? Number of object B. Let's put that this way. Number of object B. So I kind of know what I need to do, right? There's mass of A. There's a number of object B. I got to multiply by the 1 on the molar mass of A, and then I got to multiply by the mole ratio that has the number of moles of B over the number of moles of A, and then finally I've got to multiply by Avogadro's number. So I have to take my mass of A and then apply 1, 2, 3 conversion factors to it. So my first conversion factor is going to be the molar mass of A. So I've got to go ahead and calculate the molar mass of water, which, if you don't know by now, is 18.015 grams per mole. So I add together the mass of 2 hydrogen atoms and 1 oxygen atom, and I get my molar mass. Now I'm going from mass of A to moles of A, so I'm going to multiply by 1 on the molar mass. So there I am, 2.54 grams of water multiplied by 1 mole of water for every 18.015 grams of water. So now I am at my moles of water. My next step is to multiply by my mole ratio, and I need my moles of my B, which are hydrogen atoms, for every mole of my A, which were my water molecules. So from the formula of water, you can see that you get 2 hydrogens for every 1 water molecule. So 2 moles of hydrogen for every 1 mole of water. So moles of water cancels, leaving me with moles of hydrogen. And then finally, so that gets me there. Finally, I have to multiply by Avogadro's number. There we go. So I know that I get 6.022 by 10 to the 23 hydrogen atoms for every 1 mole of hydrogen atoms. Boom, boom, boom. And what am I left with? I'm just left with my number of hydrogen atoms. And it's going to be a big number of hydrogen atoms, right? In 2.5 grams of water, there's going to be many, many hydrogen atoms. So it was a good thing that I got a big number out of the end of this. So all I did was knew how to use this diagram and practiced plenty of problems and figured out how to use this diagram, and it was pretty straightforward. Okay, so let's have a look at some ALEX topics based on this idea. Now, you're going to be calculating lots of molar masses, so you want to have a periodic table present or available, or you want to be using a online molar mass calculator. So it says a chemist measures the amount of nitrogen gas produced during an experiment. Now, something to recognize is that nitrogen gas is N2 is the formula. It is a diatomic element. You can see that there, it says diatomic element. So don't forget your 7 diatomic elements. Hydrogen, and then the you go over to number 7 and you draw a 7. So it's the have no fear of ice cold beer elements. So what have we got? We've got to go from grams of nitrogen to moles of nitrogen. And so we know that to go from grams to moles, we got to multiply by 1 on the molar mass. So the molar mass of N2 is 2 times 14.01 gives me 28.02 grams for every 1 mole. So now let's do it. 40.6 grams of N2 times, we get 1 mole of N2 for every 28.02 grams of N2. So I've got more than 28 grams, so I'm going to get more than 1 mole. So grams of N2 cancels, and the answer is 40.6 divide 28.02. Boom. The answer is, we're going to do 3 sig figs. It was 14.489. So that's 8 is bigger than 5, so this is going to be 4. Whoa, that's wrong, isn't it? Oh, I see. I accidentally didn't hit the decimal point. 40.6 divide 28.02. There we go. That's better. So it is 1.44. I knew that I was wrong because it should have been, like not quite 2, right? 1.4489, etc. We want 3 sig figs, so we're going to cut it off there. So it's 1.45 moles. There we go. Better there. 1.45 moles. If you know what you expect, it's easy to detect errors. So in this problem, we're going to be using molar mass, and we're going to have to calculate that molar mass, and molar mass is the conversion factor between grams and moles. So we're going to be doing a conversion between those two things. So it says the chemical formula for barium oxide is BaO. So barium is over here on the bottom of group 2A. So barium has a mass of 137.3 grams per mole, and then oxygen is over here in group 6A, and that has a mass of 16.00 grams per mole. So to put those two things together, we can get the molar mass for barium oxide. So what do we end up with? 153.3 grams per mole is the molar mass for barium oxide. So we'll keep that to one mind, and then it's to one side. We'll put that to one side. Let me get my words right. And then it says a chemist determined by measurements that 0.05 moles of barium oxide participates in a chemical reaction. Calculate the mass of barium oxide that participates. So we're just going to go from moles to grams. And so we know that when we do that, we multiply by the molar mass. So here we go. 0.050 moles of barium oxide multiplied by 137.3 grams of barium oxide for every 1 mole of barium oxide. So there we are, moles of barium oxide will cancel out, and there's my answer. So times 0.05, and we ended up with 7.665 grams, and we need to cut this off to 2 significant figures. So it's going to be 7.7 grams, because 6 is bigger than 5, so we're going to round up in this case. Okay, so this next question is about finding formula mass given a chemical formula. So we just got to make sure that we tabulate everything okay. So this formula here is for T-butanol and is written in a slightly odd way. Normally we would never use parentheses for a molecular compound, but in this case we've got them there. So how many carbon atoms do we have? Well, we've got 1 carbon out here, and then we've got another 3 here. So in total, we've got 4 carbons. And then how many hydrogens do we have? We've got 3 times 3, that's 9 there, and then we've got another one there. So we've got 10 hydrogens. And then finally, we have 1 oxygen out there. So carbon is in group 4A and has a mass of 12.01. Hydrogen's in group 1A and has a mass of 1.008 according to this periodic table. And then oxygen's over here in group 6A, and we have 1 of those, and that's got a mass of 16.00. So the molar mass of T-butanol is 4 times 12.01 plus 10 times 1.008 plus 16 equals 74.12 grams per mole. And see here it says not the number of sig figs, but it says to 2 decimal places. And that means that we need 2 digits coming after the decimal point, which is what we have in the answer here. Okay, so here is another one. It says interconverting between numbers of atoms and mass of compound. So if we're going to go from a number of atoms, we're going to go to moles of atoms, and then we're going to go down, we're going to use a mole ratio, and we're going to go to moles of compound, and then finally we'll be going on to mass or grams of our compound. So this is going to be our first problem where we use a mole ratio. So to go from number of atoms to moles, we're going to multiply by 1 on Avogadro's number according to our little flow chart for doing these conversions. And then to go from moles of atoms to moles of compound, we're going to multiply by the appropriate mole ratio, because that's how you do moles of one thing to moles of another. And then to go from moles of compound to the grams of compound, we're going to multiply by molar mass. So if you've got that little diagram with the 6 boxes on it, you should be able to figure out all of the conversion factors that you're going to be needing. So what we're going to be needing though is the molar mass of our compound, which is this guy in here. So it says calculate the mass of diphosphorus pentoxide that contains 1 trillion or 10 to the 12 phosphorus atoms. Be sure your answer has a unit symbol, so it's going to be mass in grams, and round it to 2 significant figures, and that's because we're only going to be doing multiplication and division, and our starting number had 2 significant figures. So let's see what we can do here. But before we get going, let's go ahead and get the molar mass of phosphorus pentoxide. So we'll head on over to our molecular weight calculator. We've got 2 options. We could look to see if it's in the list, and it's not. So and then we'll go P2O5. It's not really worth looking in the list for real simple things, and it's 141.94. So 141.94 grams per mole. Okay, So now we're in business, and we're just going to set this up all in one go. So we're going to use Avogadro's number, followed by the mole ratio, followed by the molar mass of P2O5. So look how we're going to do this. So we've got 1 by 10 to the 12 P atoms. Now I'm going to use Avogadro's number, and for every 1 mole of phosphorus, I know that there is 6.022 by 10 to the 23 phosphorus atoms. So there's my first conversion factor, and that gets me to moles of phosphorus. Now I'm going to multiply it by this. I get 1 by the mole ratio. I get 1 mole of P2O5 for every 2 moles of phosphorus. So that's going to take me to moles of P2O5. And then finally, my last conversion factor, I know that I get 141.94 grams of P2O5 for every 1 mole of P2O5, and you can see that that cancels out and gives me grams of P2O5. So I'm going to put all of that into my calculator, and then I will round off to 2 significant figures. So it is 1 by 10 to the 12 times 1 on Avogadro's number, 6.022 by 10 to the 23, times 1 on 2 for the mole ratio, times 141.94 for the molar mass. And so it ends up being 1.2 by 10 to the minus 10 grams. Now that's not very surprising, because 1 trillion phosphorus atoms works out to 500 billion P2O5 atoms, which would be 5 times 10 to the 11, which is a lot less than a mole. By a long way, it's a lot less than a mole. So it should be a really, really small number, and it turns out that it was. So we don't have very many grams of P2O5 there. Okay, so that concludes this little section where we learn how to use the molar mass. Molar mass is the conversion factor between grams of a substance and the moles of that substance. And when we want to go into moles, we're going to multiply by 1 on the molar mass, and then when we want to go from moles to grams, we multiply by the molar mass itself.